In statistics, we spend a lot of time focusing on the average, but sometimes consistency is the real goal. We need to mathematically test claims regarding the variance, or standard deviation, of a population. When testing claims about means or proportions, we rely on the familiar, symmetric normal and t-distributions, but variance requires a different approach. To calculate the variance of a dataset, the underlying formula requires us to square the values of the deviations from the mean. Because squaring any non-zero number yields a positive result, a negative variance is mathematically impossible. This means the classic symmetrical bell curves extending below zero on a number line will no longer work. To test variance, we use a probability distribution built specifically for these constraints, the chi-square distribution. Before applying it, we lock in notation. Sample size n, standard deviation s, and variance s squared map directly to population parameters, sigma and sigma squared. Analyzing standard deviation accurately requires shifting into a non-negative, right-skewed statistical framework. This chart shows the chi-square distribution. As you can see, all values are non-negative, bounded by 0 on the left, and the distribution itself is not symmetric. It leans to the right. Furthermore, the chi-square is not a single static curve. Its shape is dynamic and dictates how the test will behave. This graph illustrates how that shape changes based on the degrees of freedom, which is your sample size minus 1. Notice the taller peak for 10 degrees of freedom compared to the flatter, wider curve for 20. When reading standard reference tables for this distribution, each critical value corresponds to the cumulative area to the right of that value. To use this distribution for hypothesis testing, your data must pass two prerequisites. First, the data must be drawn from a simple random sample. Second, the underlying population from which you draw that sample must follow a normal distribution. Take that second requirement seriously. Unlike tests for means, which can tolerate slight deviations, this requirement is strict. Even slight deviations from normality will invalidate a chi-square variance test. Let's test this. The U.S. Mint implemented a new manufacturing process designed specifically to make the weights of its quarters more consistent. Their historical specifications dictate a mean weight of 5.670 grams, with a standard deviation of 0.062 grams. We need to verify the Mint's claim that this new process actually reduces that standard deviation, using a 0.05 level of significance. They pull a simple random sample of 24 new quarters. When weighed, this batch yields a sample standard deviation of roughly 0.048 grams. To execute the math, we use the chi-square formula, sample size minus 1 times sample variance divided by population variance. We plug our values directly in, 24 for n, our sample standard deviation squared in the numerator, and the 0.062 variance in the denominator. Having the formula and the raw data is only useful if we first verify those statistical prerequisites. We must first confirm our 24 quarters were drawn from a normally distributed population before we can rely on the test statistic. This chart is a normal quantile plot, generated straight from the measured weights of our sample. Because the plotted data points follow a reasonably straight line pattern with no obvious outliers, the sample satisfies the normality requirement. Now we translate the Mint's specific claim into math. The standard deviation is less than 0.062 grams. That becomes sigma is less than 0.062. Because that expression does not contain inequality, it becomes our alternative hypothesis. Since the inequality symbol points to the left, we structure this as a left-tailed test. The null hypothesis then acts as the assumption of the status quo, the statement that the standard deviation remains exactly 0.062 grams. With the strict normality assumption fully verified and both of our hypotheses firmly locked in place, we can now execute the mathematical test. When testing claims about variance, the p-value, critical value, and confidence interval methods are mathematically equivalent. They will always yield the same conclusion. Processing the raw numbers through our test statistic formula yields a final chi-square value of 13.795. Executing method 1, we run that test statistic through software using 23 degrees of freedom. This gives us a p-value of 0.0674. We compare that p-value to our 0.05 alpha level. Because 0.0674 is larger, we fail to reject the null hypothesis. This visual maps method 2, the critical value approach. For a left-tailed test with an alpha of 0.05 and 23 degrees of freedom, The table sets a cutoff at 13.091. Plotting our test statistic of 13.795, it lands completely outside that green rejection region. Because the test statistic falls outside the critical zone, Method 2 also dictates that we failed to reject the null hypothesis. Both of these comparison tests align perfectly. That leaves only the boundary testing method to act as our final mathematical confirmation. For Method 3, we construct a confidence interval. A one-tailed test at a 0.05 significance level requires us to construct a 90% confidence interval to match. Processing the sample data generates a confidence interval indicating the true population standard deviation is between 0.03888 grams and 0.06365 grams. When we analyze this result against our initial baseline, the historical standard deviation of 0.062 grams falls directly inside this range. This explains why we cannot support the claim. Because the historical 0.062 value remains a plausible outcome within this range, we cannot statistically prove the new process is more consistent. This third method confirms exactly what the p-value and critical value methods found. We fail to reject the null hypothesis. Translating this statistical outcome back into plain English gives us our final answer. There is insufficient statistical evidence to support the claim. The U.S. Mint's new process has not provably reduced the variation in quarter weights.